All right, here's day number 2 of the alternating series test. We're going to use AST to approximate sums. Again, remember that I said that if you want to figure out what something adds up to, the only tests that really do that are telescoping and geometric. But we can get a little creative with AST. All right, to illustrate this, I'm going to start with a fairly basic, fairly easy alternating geometric series. You can see what's happening here. We're multiplying by -1/2 every time. And so if you wanted to figure out what the actual perfect answer was, you would use the geometric sum. This does converge because, again, r is -1/2. That's between -1 and 1. So it's going to converge to term 1, which is 32 over 1 minus r, or 1 minus -1/2. And you can see that that's going to work out to 21 1/3. All right, so that's the true answer. Now let's say that you only felt like adding part way. Let's say you wanted to add the first 5 terms together and then you got bored with it. That would be the sum of the first 5, or S5, the fifth partial sum, which happens to add up to 22. Now 22 is not a bad answer. Remember that the perfect answer was 21 1/3, so 22 is not too far off. The error would be 2/3. Now notice that this 1 is green. It's kind of weird. The 1 has a name. It's called the first neglected term. Remember, from algebra, terms are separated by addition and subtraction signs, so I don't include the minus with the term. The error that you have is 2/3, which is less than that 1. Interesting. So we are within 1 of the true answer, which again is up here. All right, let's add a little further this time. Let's say we added the next couple terms on and we have the 7th partial sum, or S sub 7. That adds up to 21 1/2. Again, remember that the perfect answer is 21 1/3. That's an error or a difference of 1/6. And 1/6 is less than this green 1/4. So I know just by looking at the first neglected term that the answer that I got here, this 21 1/2, is within 1/4 of the real answer. And in fact, it is within 1/4. It's 1/6 away. Which brings me to the key point of this lesson. The error that you get, remember, error is how far off you really are. It's the difference between your answer, the partial sum, and the true answer, if you were to add all the way to infinity, which can be found by the geometric formula. The error that you get will always be less than the absolute value of the first neglected term. And actually, I don't need to say absolute value because remember, terms don't include the pluses or minuses. So really, the error you get is less than the first neglected term. The alternating series remainder is what you want to call it. It's also called the alternating series error bound. It's also called the Lagrange error bound. So if you see Lagrange, that's the same thing. It basically just says this. If you have an alternating series, this has to be an alternating series, and of course it has to converge, otherwise you can't use that geometric formula. If the series is getting smaller, without the negative signs, of course, if it's decreasing, then you can say that the partial sum that you're taking, it's this right here, S5, S7, Sn. Actually, here, let me just make this common English here. This right here is the error. Hopefully this is going to make sense. S is the pure sum. That's what you would get. S is the answer that you would get if you were able to add to infinity, which of course is impossible. All right. Let's say you only added the first 5 terms together. The real answer minus your lazy answer is how far off you are, which is the error. And we put it in absolute value, that way that if the error is positive or negative, we don't care. The error is equal to what we call the remainder. And that's going to be R sub n. The remainder is everything that you blew off. Let me back up a slide. S of 5 is, of course, the first 5 terms added together. Everything else that you didn't include is called R sub 5. That's the remainder. That's the stuff that you blew off when you added the first 5. Same thing here. Down here, this is R sub 7. So this is that the error that you get, which is equal to the stuff that you blew off, the remainder, the error is less than or equal to the first neglected term. First neglected term is that. So if you added up the first 5 terms, the error is going to be less than or equal to A6, because that's the first term that you didn't use. Okay, hopefully that makes some sense. If it doesn't, hopefully I can make some sense to you by some examples I'm about to do. Okay, here's a problem I created. Approximate the sum of this series, it is an alternating series, by using its first 6 terms. So what I did for you guys is I listed the first 6 terms in. I plugged in a 1, then a 2, then a 3, all the way up to plugging in a 6. All right, so if you take the first 6 terms and you add them all together, if I write this out, let's see, this is going to be 1 over 1, 1/2, 1/6, 4 factorial. You're going to start to memorize the factorials involuntarily because we're going to end up using them so much. 6 factorial happens to be 720. I'll put the alternating signs in. I think at this point I'm just going to throw this into the calculator. If I had to get common denominators, I could. It's going to end up being 91 over 144. The error is going to be less than or equal to the first term I left off. And the first term I left off when I chopped this was 1 over 7 factorial. And 1 over 7 factorial is 1 over 5040, 5040. What this tells me is if I use 91 over 144, I know that I'm going to be within 1 5040th of the correct answer. So I'll just go plus or minus. It's like when you hear those political polls and they're like, hey, candidate A has a 57% approval rating, plus or minus 2%. What that means is you just add or subtract the 2 and you know that you're for sure between those 2 percentages. Same thing here. The actual sum here, we cannot figure out what it is, but we do know that if we go 91 1/44 plus 1 over 5040, that'll be that number. And if we go 91 1/44 minus 1 over 5040, that'll be this number. The sum is 0.63 something. We've got it narrowed down. And that's the best we can do. If we need to be more accurate, no problem. Just don't use S sub 6. Maybe go ahead and go out to S8, S9, S10. What will happen is these 2 numbers will become closer and closer and closer together. It's almost really a form of the squeeze theorem, and you can get a more accurate answer. Kind of like George Riemann, when he started making more rectangles, he got a better, approximation. These 2 numbers became closer and closer to each other. So, all right, let's do another. The directions here say approximate the sum of the series by using its first 5 terms. Well, the first thing I want to do is list the first 5 terms. So I'll plug a 1 in. That makes 1/11. Now the 1/11 is positive because the 1 also goes into here. That makes -1 squared, which is positive. But when I plug a 2 in, this will be a negative number. It's going to be -1 to the third. So this will alternate when I do the first 5 terms. And there's always going to be a 1 on top. All right, if you plug the 2 in, your denominator will be 14. Plugging in the 3 will give you 17. And I think you can see the pattern. It's just going to increase by 3 each time. So I can do this. All right, I am completely disinterested in getting a common denominator here. Can you blame me? So I won't. This is going to be what we call S5. It's the fifth partial sum. You could just use your calculator. The quickest way is to not go into all those sub-menus. Just simply add those 5 fractions together. It's going to come out to 0.07178230098. I hit math fraction and my calculator was like, I'm not doing that. So it wouldn't even convert it to a fraction. So I just have that. All right, the true sum in the middle here is going to be between 2 things. And I use this 0.07178 to kind of help me. I add and subtract the first neglected term, which in this case is 1/26. Because if I had kept the pattern going, that would be the first one that I didn't have. If you take the 0.07178 and you add 1/26, you're going to get 0.1102. There it is, super accurate. And if you were to take the 0.0717823 and subtract 1/26, the first neglected term, you would get 0.03332. And so we know that the actual sum is somewhere in between those 2 decimals. Now, admittedly, that's not very impressive. I'm like, hey, we're between 0.03 and 0.11. But again, I only added up the first 5 numbers. If I added up the first 10 numbers, first 15 numbers, the 2 blue decimals would become much closer, and then people would start taking me seriously and be like, oh, okay, he's actually figured out what this adds up to, without going all the way to infinity. And usually if you add 15, 20 numbers up on the calculator, you can get the decimals very close to each other. Just depends on how accurate you need to be. All right, number 8 and 9 involve a little bit less computation, which is nice. It says determine the number of terms required to approximate the sum of the series with an error of less than 1/1000th. That's 0.001, 1/1000th. Well, we're basically using the alternating series error bound here. Let's go ahead and write a few terms out as we start. If you plug the 0 in, of course 0 factorial is defined to be 1. And -1 to the 0, anything to the 0 so far is 1, so that's 1/1. Minus, and you can tell that this is going to go back and forth because of the blinker, if you will. So let me just do the easy part first and write a few terms out. I don't know if I have enough yet. I can always go to the next line if need be. All right, so we've done 0 factorial already. 1 factorial is also 1. 2 factorial. 3 factorial. 4 factorial. Yeah, we need the error to be less than 1/1000, so we have a little ways to go yet. I'm only to 1/24th, so let me continue on. The nice thing about factorials is they do start to increase very quickly. So 120, 6 factorial will be 720, 7 factorial is up to 5040, and I can stop right there. I don't need the last couple terms at all, because my error is going to be less than or equal to the first neglected term, which is 1/5000.
I just simply need to be within 1/1000th, so I'm good. All right, let's see how many terms we have. We've got 1, 2, 3, 4, 5, 6, 7 terms is the answer to number 8. Here's a similar problem, number 9. Again, we have an alternating component, which means that we can use the alternating series bound. We have to be within 1/1000th once again. That's 0.001. So we're looking for our first neglected term to be less than 1/1000th, and then we can stop. Okay, if I put the 1 in, not that it completely matters, but I'll start with a positive 1 up top. And then we subtract, and we're going to go back and forth for a little while once again, just like we did on the last problem, alternating the signs, which allows us to use this alternating series error. All right, I'm hoping this will be good enough. We hopefully won't have to use all those. Okay, starting with 1 this time instead of 0 is our index. Putting the 1 in, 3 times 1, 3 plus 2, that's going to be 5. So 1/5. Now a 2. 2 cubed times 3 plus 2 more. I got 26 for that. Let's see. Well, we're up to 3. 3 cubed times another 3. That's 81. Plus 2 is 83. That's about as far as I can go. I'll try one more. Gosh. 4 cubed. 64 times 3. That's 192 plus 2 is 194. Yeah, I'm not up to 1/1000th yet. Let's give the brain a break and use the technology. My goodness. I'll just take this 3n cubed plus 2 and put it into the graphing calculator. Why not? There we go. Brilliant. And then I can just look at the table. And I can see the numbers that I've already worked so hard to come up with. And I can see that really I only have 3 more to go. 377, 650, and then 1031 could be neglected. I can stop right there. So you can see that the answer is going to be 6 terms. Let me fill in the rest just to be official. So we had 377, 650 was in the chart, and then I saw 1031, which is a stop sign in my book, and we just have to count them up. I believe there were 6. 1, 2, 3, 4, 5, 6. Yes! 6 terms required to get an answer that we know is within 1/1000th of the true answer. All right, great. What's really great is we're going to take a break, and we'll come back for the third and final day of this section, the alternating series test.